There are jobs that test a machinist's skill. And then there are jobs that test everything. Their patience, their nerve, their instincts built up over decades at the bench. What you're about to watch is the second kind. The part sitting on the workbench right now is the engine mount pulled from a crashed Bugatti Chiron, one of the most exclusive, most expensive, and most unforgiving hypercars ever built. And it's broken. Snapped clean. An entire multi-million-dollar rebuild has ground to a complete halt because of this single component. The team has tried everything to move forward. They can't. Not without this piece being fixed first. So they called Bob. Bob is a specialist. Not in the way the word gets thrown around loosely, he is the real thing. A machinist and welder whose career has been built on solving problems that other shops quietly decline to take on. When a part lands on his bench, it doesn't leave until it's right. That's not a policy. That's just who Bob is. He picks up the mount and turns it slowly in his hands. His expression doesn't give much away, but you can tell he's already thinking 3 steps ahead. The damage is significant. The mount has fractured through its main body, not a hairline crack you might overlook on a quick inspection, but a full structural break. And it's not the only issue. Some sections of the aluminum show a dull, cast texture that's been disturbed and hammered looking. Bob's read on that? After the crash, the car was driven. Briefly, but enough. The engine vibrating against a compromised mount repeatedly stressed the same fracture point until the cracks spread further. The part didn't just break once. It was being broken, slowly, every time the engine fired. This isn't a simple fix. But Bob doesn't do simple. Before any welding begins, there's a complication he has to deal with first. Earlier in this project, the part was sent out for 3D scanning, a smart move, since the team wanted to explore whether a new mount could be machined from billet aluminum. To get a clean scan, the 2 broken halves had to be held together temporarily. That meant tack welds. Quick, rough, just enough to hold the shape. The problem? Those tack welds are holding the mount in a slightly distorted position. There's a small but measurable gap along the fracture line, a few millimeters wider than the original geometry. Before Bob can do anything meaningful, those temporary welds have to come off and the piece has to be allowed to settle back into its natural alignment. He starts grinding. Carefully, deliberately. Every pass of the tool is controlled. Bob knows that the fracture surfaces themselves are alignment references. Damage them and the whole repair gets harder. The goal here is purely to remove the weld material and any deformation from the impact, nothing more. With the tack welds removed, Bob places the 2 halves together and immediately notices something. There's a slight rocking motion, like a seesaw. The outer edges of the fracture make contact, but the center sits just a hair too high. The crash bent the casting, barely, but enough to prevent the surfaces from sitting flush. Bob addresses this methodically. Using a wire brush and careful light preparation, he removes only the absolute minimum material needed to eliminate the rock. A few minutes of work. A few targeted passes. He tests it again. And again. Then, it stops rocking. The mount sits flat. Every reference point contacts simultaneously. Bob checks it once more, then sets it down with quiet satisfaction. That's the kind of moment you don't fully appreciate unless you understand how much precision just went into what looked like an almost invisible fix. Across the fracture face, there's nearly 300 millimeters of contact surface to deal with. Bob deliberately leaves several key areas untouched by power tools. These will act as natural registration points. Every time the 2 halves are assembled, they'll return to the exact same position. That consistency is critical for what comes next. Now comes the question that has been hanging over this entire project from the beginning. Can this alloy actually be welded? The mount is cast from A357 aluminum, a high-strength alloy containing silicon and magnesium, commonly used in aerospace and high-performance automotive applications. In theory, it's weldable. In theory. But cast aluminum is notoriously tricky. Porosity, contamination trapped inside the casting, unexpected alloy behavior under heat, these are the things that can turn a promising repair into a cracked, ruined mess. No amount of planning fully answers the question. Only a real test weld will. Bob sets up the test. He selects 4047 filler rod, It flows more smoothly than the alternative 4043, which matters here because the geometry of the repair will require some gap filling. He's also planning to add reinforcement plates, so the raw strength of the filler rod matters slightly less than its workability. He strikes the arc. For a few seconds, nobody breathes. The weld pool forms cleanly. The bead lays down smooth and consistent. As the aluminum melts, tiny bubbles rise to the surface, magnesium within the alloy burning off as the impurities escape. It's normal. It's expected. And the weld holds. Bob lifts the torch and inspects the result up close. The bead is tight, well-fused, structurally sound. The casting is weldable. The repair can proceed. Bob moves to the milling machine. Before a single final weld is laid down, he needs precise measurements. A bore running through the center of the mount acts as the primary reference point. By finding its exact center, Bob can measure outward to key features on both sides of the fracture and confirm the part is properly aligned. Here's where it gets interesting. As he clamps the mount to the milling table, Bob notices something unexpected. The casting isn't perfectly symmetrical. One side sits slightly differently than the other relative to the table. This isn't the result of damage, it's how the part was designed. The original Bugatti component has an intentional asymmetry built into its geometry. That changes things. It means Bob can't rely on visual symmetry as a check. He has to measure everything precisely with no shortcuts. Using an edge finder, he probes the metal surfaces with a spinning tool that detects the exact position of each edge. Slowly, carefully, he builds up a map of the mount's geometry and compares measurements on both sides of the fracture. Some features can't be reached directly, so Bob works around them, using nearby reference points to reconstruct the geometry. The result? A difference of just 0.6 millimeters across the entire part. Each side is off by roughly 0.3 millimeters. For a component of this size and complexity, on a part that was broken and manually realigned, that number is extraordinary. Bob nods slowly when he sees it. Good enough isn't in his vocabulary, but this is genuinely excellent. The final welding stage is where everything comes together or falls apart. Bob begins by preheating the entire component to around 200 degrees Celsius. This is non-negotiable with cast aluminum. Welding a cold casting creates violent thermal gradients, the metal expands unevenly, and the stress cracks what you're trying to fix. Preheating brings the whole part up to a stable temperature so the heat from the torch doesn't come as a shock. Once the mount is up to temperature and clamped securely to the welding table, Bob begins the main weld sequence. The chamfered edges along the fracture allow the filler material to penetrate deep into the joint, not just a surface bond, but a fully fused connection that runs through the thickness of the aluminum. The weld pool moves cleanly. The 4047 rod flows exactly as Bob expected. There are few impurities, a testament to the quality of the original casting. Bead after bead, the fracture disappears under solid, consistent aluminum. When the main welds are complete, Bob isn't done. He fabricates reinforcement plates, carefully shaped to the internal geometry of the mount using cardboard templates, and welds these into place over the areas that were most severely damaged. These plates don't just add material, they fundamentally change the load distribution around the repair. In the end, the repaired section may well be stronger than the original casting. With the welding finished, Bob sets the mount aside and surrounds it with welding gloves to retain heat. The part needs to cool slowly. A rapid temperature drop after welding could introduce warping or residual stress that undoes everything. Controlled cooling, gradual and even, is the final step in the process. After cleaning, the mount goes to precision measurement, probed by a coordinate measuring machine that physically contacts key points and records their exact positions. This isn't a visual check. Sensors near the engine depend on the mount sitting in exactly the right location. Even small deviations can cause issues at the extreme RPMs a Bugatti Chiron produces. The measurements confirm what Bob already suspected. The repair is accurate, the geometry is correct, the part is ready. A pass through the vapor blasting cabinet restores the surface to a clean, uniform finish. The mount looks factory fresh. Bob sets it on the bench and takes a long, quiet look at it. This is the part that stopped an entire rebuild dead in its tracks. The part that no one knew could be fixed. And now, it's fixed. There's one more detail worth noting. The location where the mount broke wasn't random. It may have been designed to fail exactly there. In high-performance engineering, certain components are intentionally made as sacrificial parts. They absorb catastrophic force and break so that more expensive, harder-to-replace systems survive. On a car where the engine alone can cost millions, a mount that fractures cleanly in a crash isn't a failure. It's doing its job. Whether by design or by consequence, that mount protected the engine. And now Bob has given it a second life. The Bugatti rebuild continues.